Hello students. So this is lecture number 4, okay, and we are into chapter number 2 only, okay. So far we looked at 2 examples. So first one was the spring example, number 2 was the resistance, right? Okay. Okay, today we will look at different examples. Okay, more types of examples. Okay, and this will be the spring was more mechanical, right? This was a mechanical example. The resistance or network of resistors was electrical example. Yeah. Okay, now we can also from the mechanical also we can have different type of examples could be like of heat transfer, could be fluid, okay, fluid mechanics example, okay, could be mass transfer, okay, mass transfer, basically what we diffusion basically we are talking about, and even could be even more like Poroelasticity example also could be there. Yeah. Okay. So basically the different uh, from mechanical only, but as long as we have this kind of relation where there are two ends and there are two properties, let's say it's u1, it is a u2, okay, and there is some property, let's say f, that depends on the difference of the two, right? So let us say this, if this is f here, that depends on the u2 minus u1. This kind of relation, as long as we have this kind of relation where there are f, this one is equal to k times like u2 minus u1, this kind of relationship, as long as you have, you can formulate the problem in terms of finite element analysis. So basically this kind of relationship is important, and once you know that, you can go ahead with the formulation. Okay, so let's look at these things, okay, one by one. Let's see, and accordingly we will find out how we can do it. Okay, so let's say start with the heat transfer. So heat transfer, there is something called Fourier law, and this tells that if, let us say, if there is a bar, something like this one, yeah, and like this, and let us say there is a the area, okay, so area, so this is the area, so area is a, length is l, okay, and there is temperature, this is temperature is node number 1, then node number 2, temperature is T1, here temperature is T2, okay. So it says that the Q, that is heat flux, is equal to, it says, is equal to K times A times T2 minus T1, sorry, T2 minus T1, okay, then divided by L. So basically this tells you Ka, actually this tells you dt over dx basically, if it is x in this direction. This is a differential equation form, but this we will see later on in differential equation form. But right now we are talking about the discrete system, where we are actually not talking about the differential equation, but rather we are talking about this kind of form, where this is a kind of discrete system it becomes. So you have q that depends on the two difference in the temperature here. So this is temperature. Okay. So this one also we can write this q. If you see the units wise, this q has units of watts. Okay, so this will be like a joule per second. Okay, joule per second. Okay, so like watts. Okay, so this tells you how much energy is entering, basically passing through this element. That's what it's telling you. That's what q is. Yeah. Okay, now this k is the thermal conductivity. Okay, and rest of the things we know. This is the area of cross section. Yeah, so let's write that also. So this A is the area of cross section. Okay, and we know these are temperature T1, T2, and length is L. Yeah, so this is given here. Okay, so let's now formulate the problem. Let's write it in terms of the Ku equal to F type of thing. Okay, so how we will analyze the same way as we did earlier. So let us say this is a, how are you going to do if T equal to 0 here. Yeah, and if you have a temperature here, like let's say T1 equal to 0 and T2 is given here, and then we will see that since we are assuming T2 is greater than, okay, just for derivation we are assuming this is a convention basically. So let's say this is T2 is greater than T1, so that we give the correct direction for Q. So this is how Q2 looks like, right? Okay, so we have T1, let's make it 0, then we have T2 here, so let's assume T2 is greater than T1, so that is T2 greater than 0. If the temperature is at higher level than temperature at first node, that means energy has to flow from here to there. That really means the energy flows from higher temperature to lower temperature, right? So Q2, that really means will be equal to what? Thermal conductivity. So this is K times A, right? And then we have T2 minus T1 divided by L. Yeah, so that's what we get, and this is the positive direction coming into the system is the positive direction, right? So positive direction means this is our convention. This is how we are. If you look at our derivation, we have assumed this way, means if T1 is 0, if T2 greater than T1, then since the energy flows from higher temperature to lower temperature, so Q2 is positive in that case. It will have positive value, and that value will be Q2 equal to Ka multiplied by T2 minus T1 divided by L. So we got that. Yeah. Similarly, we can, if we are writing like this one, we can also write the second example where we are making T2 equal to 0 and we have T1 here, and again we are if you assume T1 is greater than T2 which is equal to 0, and in that case the energy will flow from this side and Q1 will be is equal to this will be positive. Yeah, so if Q1 is positive, we can write Q1 is equal to again K times A, and then we write at T1, yeah, and then minus T2, right. So T1 minus T2 divided by L. Yeah. Okay. So we can combine these and these equations. We have two equations, and that we can write. And how we can write? We can write like this. We can write like K A over L. Then we have 1 minus 1 minus 1 1 multiplied by T1 T2 is equal to Q1 Q2. Okay. So this equation Q2 okay, let's go one by one. So Q1 this one we are talking about equal to Ka over L. So K over L we have. Then it says T1 minus T2. So we have T1 multiplied by 1 and minus 1 multiplied by T2. So this makes it, this multiplied by this makes it T1 minus T2, right. Okay. Similarly, the second equation, if you see Q2, this Q2 is equal to Ka over L. So Ka over L, then T2 minus T1, or minus T1 plus T2 is the same thing, right. So we have T1 multiplied minus 1, so minus T1 plus T2. So this becomes T2 minus T1. So we get this equation, and this is in the form of the matrix system, like we used to write. This will be equal to K U equal to F, where K is equal to Ka divided by L, 1 minus 1 minus 1 1, right. Then we have U is equal to nothing but T1 T2. Okay, transpose of that we are writing this way. Okay, and then similarly F will be equal to Q1 Q2 is the F. Yeah. So this is what we got. Once we have this one, you know what to do. If you have a complicated problem, you can now apply it. So this thing is assemble it, you know, and you go from there. Okay. Now we have this formulation. If you have any, you can solve any problem now. Let us say you have a heat transfer problem where this is something like this one. So let us say okay, let's say there are 3 bars. Okay, so this is number 1 element, this is number 2 element, number 3 element. Okay, this has area A1, okay, and L1, length L1, then conductivity K1. Similarly, this will have A1, A2, sorry. So A2, L2, K2. Similarly, third one have A3, L3, K3. Okay, so these are the nodes. Okay, so let's say your example is T1. Say this is temperature T1. This is node number 1. node number 2 T2, this is node number 3 T3. Yeah, so since this is node number 1, this is node number 2, node number 3, and hence we for this one the we can write the big K. The big K we can write like this. You can see here the first element has from 1 to 2. Yeah, so we can write just assembled one, right? So we can write K1 A1 over L1. Okay, so this is between 1 and 2, node 1 and 2, right? So hence we have like this, then minus K1 A1 over L1 minus K1 A1 over L1 plus K1 A1 over L1. Done. So this is done. Now number 2 is between 2 and 3. Yeah. So accordingly we can write it here. 2 and 3. So we can in fact we can write here like this is 1, this is 2, let's have 3 here, similarly 1, 2, and we have 3 somewhere here. Okay. Okay, so okay, so we will have here K2 A2, then L2, then minus K2 A2 over L2, then we have minus K2 A2 over L2 plus K2 A2 over L2. So this we have done, which was between 2 and 3, and we between 2 3 we wrote. So hence we have this one written there. Okay, now third one is between 1 and 3. So we are going to write here 1 3, right, and this and this. We are going to write here will be the third one. Okay. Okay, so this is we have to write, let's write in different. So this is about the third one. So we have to write because of this contribution here, that's really means. So we have plus K3 A3 over L3. Okay, then we have minus K3 A3 over L3. Okay, here also minus K3 A3 over L3, and here will be plus K3 A3 over L3, right? Okay, and hence we get this. Okay. Okay, so this is how you get the distribution matrix. So what we have done for the first element, we are writing here, 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 here. From the second element, it will add between 2 and 3. So we are 2 3 2 3, right? So this is 2 2, this is 2 3, this is 3 2, this is 3 3. For the third one, this is between 1 and 3. Hence number 2 we did not touch because number 2 is here, and this is connected between 1 and 3 only. So 2 we don't write anything. The remaining 4 where we will be writing the 4 entries. So you have we added here plus K3 A3 over L3 minus K3 A3 over L3, here also minus, and here it will be plus. Yeah, so this is how you get the big stiffness matrix. Similarly, we can write here the displacement vector which will be equal to T1, T2, T3, the displacement vector. Okay, then force vector, we can write a force vector. So force vector F, we can write it at, so again it will be in terms of q1, q2, q3, so right, q1, q2, q3. So okay, I am writing in terms of transpose because the what we have is a row vector, but actually it should be a column vector like this one. So hence transpose I am writing here. Okay, this is how you get rest is giving the boundary condition. If you know the boundary condition, accordingly you give. If T1 is equal to 0, you will write here 0. If the heat coming to it, so Q is basically the heat coming to all these corners, right? So we can basically okay, so we can show it. So the coming here, see, will be Q1, the heat coming here, Q2, and similarly here it will be Q3. Yeah. Okay, so if there is a condition that there is no heat flowing in or out, then you will take Q2 equal to 0, right? If and similar to earlier, like either you prescribed force or displacement, similarly either you prescribe the voltage or current. Similarly here, either you will prescribe the flux or temperature, but not both. Either you know this one or this one. Based on that you will do it. So rest you can do once you have this Ku equal to F system, rest you can do, right? So we have Ku equal to F, and then based on the boundary condition you will go ahead from there. Okay. Okay, now let's look at different systems. We have already looked at the heat transfer now, so let's also show the fluid flow example. So let's look at like Poiseuille equation or Poiseuille flow, right, through a circular pipe. So if there is a circular pipe, yeah, and here also this is written as Q equal to pi r4, and then you have dp over dx, and divided by you have 8 mu, right? So you have dynamic viscosity here 8 pi, this radius of the pipe, and then you have the pressure gradient basically, right? So this you can also write this as Q equal to pi r4 divided by 8 mu, and you will have pressure gradient. So let us say the pressure here is, in fact you have minus sign, actually you write minus here, yeah, so you have minus sign because pressure gradient, fluid will flow from higher pressure to lower pressure. Okay, so hence it's like this one. So basically let's look at here, if you have pressure P1, this is P2, okay, and similar kind of derivation you can do, like let's say P1 equal to 0, yeah, so P1 equal to 0 and P2 is there which is greater than P1, right? Then what it will do, the Q will flow this way, this is the what the Q is, yeah, okay. And then you can write Q in terms of P1 and P2, and how will you write? You will write like this, Q is equal to, okay, Q will be equal to pi r4 divided by 8 mu multiplied by P2 minus P1. Okay. Why? Now here if you see, our convention is, if the fluid is flowing inside to the pipe, then it's positive, either whether this side or this side. Okay, like in current also, we assumed any current flowing into the conductor was positive. Similarly here also is like this only. Okay, and it also makes sense. You can see that if you assume the P1 equal to 0 and P2 greater than P1, hence since the pressure P2 is greater than P1, automatically Q will be flowing to the pipe only, and hence this Q will be positive, and hence we are writing like this one. So P1 is positive, all other quantities are positive, hence Q will be positive. So you are looking like that also. Okay, now similarly you can write derive for this the other way, and if P1 is greater than P2, and let's say P2, not necessarily you have to make P2 equal to 0, but just to make you understand, I am doing all those things. Yeah. So basically this, if we have P1 greater than P2 here, then Q will be entering like this one. So here we can write, this is, since we are writing at point 2, so we write Q2, so Q2 equal to like this one. Here we will write Q1. Okay, and using this Poiseuille equation, yeah, so we can write here Q1 is equal to pi R4 divided by 8 mu, right, and then we will have P1 minus P2, right. Okay, so we got both the equation. The rest is the writing this in terms of matrix, and that's what we will do. So we can write the equation will be something like pi R4 divided by 8 mu. Okay, and then we have 1 minus 1 minus 1 1, and then you have P1 P2 is equal to Q1 Q2. Yeah. Similar kind of thing we got for heat transfer also, right? We had some constant here, then 1 minus 1 minus 1 1, then you had T1 T2, now you have P1 P2. Here also you had Q1 Q2, here also. This is also flow, that was also flow, that was heat flow, this is a fluid flow. Yeah. So here also the example could be any kind, like let us say you have a pipe which is going like this, going like this one, going up. Let us say like this one, you have pipe. Yeah, so you can now you will have node 1 2 3, yeah, and then you will have 4 5 6. Yeah. Okay, so you can assume there is one pipe which is till here, then another pipe goes like this, third pipe goes like this, fourth pipe like this, and fifth like this one. So you have element 1, this is 2, this is 3, this one is the fourth one, this is the fifth one. Okay, so and then you formulate like then you have this equation, and you know that the first element is between 1 and 2, and hence in the final K matrix contribution of this will go to 1 and 2 only, for this will go to 2 and 3, this go to 3 and 4, for fourth one it go to 4 and 5, fifth, and for the fifth element it will go to fifth and sixth. Yeah. Accordingly, in this example, if you see here, there is no outer Q here, right? There is no pipe connection here. Yeah, so automatically that tells you that basically here Q2, right? This will be Q2 equal to 0 because it's not connected. Q3 equal to 0. then here q 4 equal to 0, q5 equal to 0, and the q1 and q2 will have some value, yeah, depending on, yeah. So you don't know, either you can give a pressure here or q here. Yes, the problem could be something like you are giving, let's say this is going outside with some value q. Okay, I'm writing a small q here, but what I mean is same, right? So just to mention here, q equal to q both, right? So so there is no difference. I'm not distinguishing between a small q and big q, but uh, here we can write, let us say q6 equal to 5, let us say, and here we can say p1 equal to say equal to 8, we can write like that. Yeah, accordingly we have to find out, uh, here you can find out what is the pressure here, what should be the pressure here, what will be the pressure here, what is the pressure here, and so on. We can write, yeah. Okay, by we can solve basically the way we have solved for others, we can also solve like this one, yeah. Okay, so I'm just introducing you to the problems basically where you can apply and deriving the Stephenson matrix. This is the Stephenson matrix here, right? So the Stephenson matrix, a small k element Stephenson matrix equal to pi r4 over 8 mu, and then 1 minus 1 minus 1 1, right? Okay, so once you know the Stephenson matrix for one element, rest you can do, rest is assembly only, the way we have been doing. Okay, now let's look at other problems as well. So other problems could be, say what is not a mass transfer, okay, or diffusion, basically diffusion. And diffusion is like there's something known as Fick's law, and this tells basically, again here there will be a q term coming, so there will be q, yeah, is proportional to or equal to minus d and then dc over dx, something like that it says. So what is that? This is basically q, where q, let's write also, this is the flux, yeah. So the flux, this is flux, and this is mass transfer. So typically some ions or something that flow per unit, or you can say flow or mass flow, okay, flow of mass or a species or anything, yeah. Typically this is number of moles, right, number of moles per unit, let's say flow of ions or a species, rather, so called a species, that's how they write it, species per unit area per unit time, yeah. Okay, this big D is known as diffusivity. So this is diffusivity, okay, and this one is dc over dx will be a concentration gradient, okay. So sometimes they also write psi instead of c, you write psi also, okay, so like that. Again what you see is some quantity written as equal to some constant and then gradient. Again similar pattern. If you see, all are based on flow only, right? So whether it's a flow of liquid or flow of heat or flow of some ions or something, yeah. Okay, so this you write like I, this will simply sometimes it could be in terms of moles per area per unit time. So either you can do like this one, or you can also have some different kind of units. Okay, and similarly this one, the C will be as moles per volume kind of, right? So accordingly uh, all will be like they should be they should have a the what I mean to say, they should all follow a SI unit, or so depending on what the unit of this and this, you will decide the unit of this, or what unit of this and this, you will decide the unit of this. So basically, as long as you are giving the number and you know what they mean, okay, so accordingly you will get the results. Okay, so here just looking at it, you can actually derive also. Okay, so the how will you derive? So this we can do like this. So let's go, yeah. So here also we can have, say, C1 here, C2 here. Let's say concentration C2 greater than C1, greater than C1. Then you know that the diffusion happens from the higher concentration, so lower concentration. So we can write here the Q, right? So this is Q2, there will be Q2. So Q2 is Q1 will be here. So just write Q2. Q2 equal to will be equal to D. Okay, for diffusivity, then we will have C2 minus C1. Okay, so this telling us the concentration C2 minus C1 and divided by L, Why L? So if you see here, it says dc over dx. So if we have a length L and difference is C1, C2 and C1, difference of concentration divided by length is dc over dx only. So that's what we are writing like this. Yeah. Okay. Okay. In fact, we can whenever we talk about like this one, this q, a small q here, that means per unit area. So we can in fact also multiply by area to mean the whole, to mean the flow of species per unit time. So it will be the total for that the so whatever volume we are talking about, for that, so through not in terms of the per area, but the total through that cross section. That's what I mean. So in that case you have to multiply by area. So if you want, now we write the capital Q, Q2 equal to, it will be D times A C2 minus C1 over L, and that really means that this will be the total through the cross sections, total flow. Yeah, so we can also write it to the total flow through the cross section, okay, per unit time, okay. And similarly here you will get this end, you can do. So basically we don't have to always write C1 greater than C2 and then derive it. Just look at here, it says Q2 equal to D C2 minus C1 L. Just looking at that, we can now write, and what will we write? We will write Q2, then we write Q1, is D, we write D, C2, we write C1, C1, we write C2, and divided by L, it will work. So Q1 equal to D, then C1 minus C2 over L, okay, and hence we can write Q1 equal to D times area, okay, and then is area of cross section for the, and we are assuming it to be constant throughout that, yeah. So area, this area of cross section is the same area everywhere, that's what we are assuming. So dA multiplied by C1 minus C2 over L, and hence we can combine this equation and then this equation together, and what we will get? We will get dA over L, and then we have C1, sorry, not C1, rather 1 minus 1 minus 1 1, and then we have equation C1 C2 will be equal to big Q1 and big Q2. So we got that. So once we have that, we know what to do. If we have a system of lot of let us say pipe or something of this shape through which some ions are diffusing, yeah, so we know we can formulate the problem accordingly, yeah, okay. Similarly, there could be the different kind of let us say the poroelasticity problem. You can also have poroelasticity and many more, okay. So these are, okay, so in that case what's known as Darcy law, and what is that? It says that, so if the medium is porous, so let us say there is something one dimensional medium which is porous, and then it says the flow, again this kind of thing, the cube term will come, the flow of the fluid is equal to what is known as equal to minus, and there will be some k, some constant divided by some mu term is there, then you have dp over dx, something like this, okay, okay, where k is constant, also known as permeability of the medium, mu is the viscosity, okay, and then this is the dp over dx is the pressure gradient, yeah. So anyway, this you can also write as equal to minus another constant, okay. So I am writing is k bar, okay, and then you have dp over dx, okay. Again, this is similar to the flow problem, you know, so fluid flow problem, so you can organize this way. So how can we write? So we can write the equation same as earlier. How? So let's say this is 1, this is 2, okay. So again this is per unit area type of thing, so we can write q is equal to minus ka over mu multiplied by dp over dx type of thing will be there. So hence there will be q1 here, yeah, there will be q2 here, right, and then we have area A throughout the same thing, then we can have a pressure P1 here, P2 here, and we will get the equation Ku equal to F type of equation, where this is for element, we are talking about the element only, where K is equal to, you can look at that, you can find out K is, okay, we are talking about this K, or let's write like this one, not to be confused. So we will write this one k bar. Okay, so getting this one, this k bar. Okay, so k bar times a, okay, and then we have 1 minus 1 minus 1 1, then u will be equal to our p1 and p2, so we write p1 p2, and then we have f, okay, and f will be equal to q1 q2. So we have formulated this one like that. Okay. Okay, so so far what we have been doing, just looking at the problem, and from the physics, from some law or something, we are finally getting this kind of k equal to f relation. So once we have this mathematics, and then after that we can go ahead, we can solve the usual way. So we have already studied how to assemble. Yeah, so we are not doing assembling part, but we are trying to understand the physics. Basically from there we try to make some matrix type of formulation so that we can solve it. Okay. Similarly, there will be the elasticity problem. Yeah, so elasticity problem, 1D elasticity problem, in which there is a bar like this, and then there may be some forces there. Yeah, so what kind of forces? So let us say, let's fix this end, okay, and then we are going to apply linear force F, let's say F here. So what is the equation? Okay, either there are many ways of solving this one. Many way meaning that either you can assume this to be a spring and see what is the force and find out deflection, or you can also do like this. We use the Hooke's law basically. Yeah, Hooke's law, and what is called, this says sigma equal to E times epsilon, and where we know that this is a stress and this is Young's modulus, and epsilon is the strain. Okay, okay, and also we know that sigma equal to F over A, right? So this is F over A. Okay, and then you have strain is equal to also delta L over L, we say. So okay, and delta L nothing but u. So whatever the, let us say this has u is the displacement. Okay, displacement. So basically this is u over L. Yeah, okay, so we get the relation, we put all these values here. Yeah, then what will you get? We get sigma, so F over A is equal to E times epsilon, so u over L, so we get u over L, and hence we get F over u, yeah, is equal to EA over L. Yeah, so which is equal to K, right? So the force per unit displacement is nothing but the stiffness, right? So that's what this is, the equivalent of K. So this K, this tells you K is nothing but equal to EA over L. So that means both will behave exactly the same way. Yeah, if this had the stiffness K, and if this is a bar of a uniform area A, and if you apply the force both of them, if K is equal to EA over L, then both will have the same displacement. Okay, okay. So so that means you can solve the similar problems, the whatever you solved for the spring, we can do the same thing. So let's say if your problem is something like this. So you have a bar here and then another bar like this one, yeah, and and you had a like let's fix this also, and you are applying a force F here. Okay, so F equal let's say F equal to 1 Newton. You have area here, some area A1, E like E1 A1 equal to 1, and here we have E2 A2 equal to half, or make it 2, let us say, yeah. And let's we want to solve it. How will we solve? Length is the same in both the case. Length is 1 and here also it is 1. Okay, so for simplicity I have taken very 1 or 2 this kind of numbers, you know. So these are all just to see how easy, I mean just to solve it easily. So how can we do it? So we start with this is node number 1, this is node number 2, node number 3, element number 1, element number 2, right? First we find out the stiffness matrix for first element for this one, and what we will get, we can write it as E1 A1 over L1, right? Because this is what the K is, right? Equivalent to K. As I said, both this and this are equivalent. This spring and this are equivalent, and how K, we can write K equal to E over L, yeah, and the rest you can assume it to be a spring and you can go ahead from there. So we have K1 equal to E1 A1 over L1, and K2 is equal to E2 A2 over L2, and which is equal to K1, it's given that E1 times A1 equal to 1, L1 is also 1, so equal to 1, and similarly K2 will be E2 A2 over L2, yeah, so that becomes 2, so we have 2 here, yeah. So stiffness matrix for what we will get, we get big matrix K equal to, we get 1 minus 1 minus 1 1 plus 2 minus 2 minus 2 2, right, and then we get 0. Yeah, why we did like that? Because see here this is connected, this element 1 is connected to node 1 and 2, so hence 1 and 2, so this is 1 2 and 3, here also 1 2 and 3. So what we get here, the first element contributes to 1 and 2 only, so this is 1, this is 1, this is 2, this is 2, so this is where it went, and then second one goes to 2 and 3, so 2 here and 3 here, 2 here and 3 here, so hence this went here, okay, and the rest we put 0, yeah. So here both have common, so hence you have 1 plus 2, right? Okay, so we got K. Now now we have to find out U. Okay, so U equal to U1 U2 U3, and what U1 is, this is fixed, so 0. U2, if is applied, we don't know what it is, write U2, and U3 again fixed, we don't know what that is. We know what that is, that's U equal to also 0, U3 equal to 0, so we write U3 equal to 0, and here also U1 equal to 0, yeah. Okay, so you get 0 like this, okay. Force vector F is equal to, here we don't know, because you have given U, we have fixed this one, we don't, there will be reaction, so we don't know what the force is, so we write just F1. So let's write F1. Then here F equal to 1 means F2 equal to 1. So we write 1, which is in positive direction, C X direction, so positive, so we wrote 1. And then here we again we don't know because this is fixed, U is given, hence F we cannot, we don't know, right. So here also we write F3. So this is what the equation is. Again, looking at it, we are going to multiply this row with this one. Why? Because finally we have to we are going to work, finally we will have the equation to be solved, which will look like Ku equal to F, and where K is this, the whole thing multiplied by U, which is like this one. So hence if you see here, it has U has 0 here and 0 here, that means it is going to multiply by this and this also. Yeah, so that means we are, since here it is 0, this is 0, so first row and last row is not relevant, and also the in order to find out U, we will not need this one, anyway it is going to multiply and make it 0. So what we get simply is, if we multiply this with this one, we are means second equation of this will be simply this multiplied by this, which will be equal to 3 multiplied by U2 will be equal to 1. Okay. So answer, what do we get? By this we will get 3, which is this one. So 3 multiplied by U2, right. So U2 is equal to F, which is equal to 1. So equal to 1, and hence this tells us U2 equal to 1 over 3. So you got the answer. Once you know this U3, you can find out other values. So now we are going to put 0, 1/3, 0, and we multiply, we want to find out F1. So we get from the first equation of this system, the first equation will be this multiplied by this equal to F1. So F1 will be nothing, since this is 0, this is 0, hence again the whatever multiplies here is 0, whatever multiplies here is 0, so we get minus 1 only. So it tells you minus 1 multiplied by U2 equal to F1. So simply it tells you F1 equal to minus U2. Okay, so we get simply F1 equal to minus U2 equal to minus 1/3, right. We get that. Similarly, we look at this last equation of this system, meaning that last equation will be this multiplied by this equal to F3. So F3 equal to nothing but minus 2 U2, right. So that really means you get you will get F2 is equal to minus 2 U2 equal to minus 2/3. That's it. Okay. So we got all this answer. You can check also whether it's correct or not. How do you check? They should balance, the forces should balance. So if you see here, if this force is going this way and which is 1 Newton, then you know that total force, whatever the force here plus this force should be 0 for balance, right. So you have here F1 is minus 1/3, then you have 1 which is plus 1, and then you have minus 2/3. So minus 1/3, 1 minus 2/3. So minus 1/3 plus 1 is will be 2/3, and 2/3 minus 2/3 will be 0. Hence all are in balance, right. So that means your answers are Correct. And you will have the displacement here which will equal to 1/3 unit. Yeah. So this is how you solve it. Okay. Okay, so that is all for today. Okay, so and what we learned today is different kind of problems, and all of them have a similar kind of relationship that can be put into a matrix system, and hence we can solve them.